Howdy, y'all, and welcome back to the channel. I am Professor Parks, and just a couple of notes. One, please pardon the dust because apparently they are working on my building, and it is at least really loud to me. So I don't know; it might pick up on the show. Also, today's lecture is brought to you by NOVAC, the Northern Virginia Astronomy Club, and here goes the last of my coffee. So, what are we going to talk about today? This is the third of my lecture series, or third lecture in my series, The Solar System, where I do a little bit of a deep dive into, the solar system, and particularly the tools that, and also, I should say, the tools that astronomers use to figure out what the solar system is and how big is it, what is it composed of, how did it form, things of that nature. So today we're going to actually look a little bit beyond the solar system, and we're going to be basically looking at two things. I'm going to be talking about two things. One, how do astronomers, or how do scientists really, deal with things that are unimaginably large or unimaginably small in terms of measurement, specifically size. You know, when we think the distance between New York and LA is roughly 4,500 kilometers. I can barely conceptualize what that is, mainly because I've driven it. It took me about two and a half days to do it. But the distance from the Earth to the moon, which is roughly 380,000 kilometers. Hopefully I don't embarrass myself and get that wrong. That kind of distance, that takes a bit for me to really conceptualize. And that's really the shortest astronomical distance that we deal with. Everything else is, obviously beyond the orbit of the moon. So how do we represent these numbers? I mean, if we were going to represent everything in kilometers, things would get ridiculous really, really fast. Another way that we deal with distances, particularly time, is that it has to deal with a fairly strange concept. And it might seem like I'm back on my friend's porch smoking a little bit, but there is a very odd thing when you really think about how things are communicated in the universe. And the reason why they're odd is because the speed of light is not infinitely fast. While it might appear to be so on the Earth, if someone down the road turned on a flashlight and you were on walkie-talkies, then they said on, and you would hear on and see the light pretty much at the same time. Well, really at the same time. But that's only because the speed of light is, from a local standpoint, very, very fast. It's 3 times 10 to the 8th meters per second. And there I go, using scientific notation before I've even explained what it is. It's really, really fast. But it's not infinitely fast. And so the weird concept, or the weird consequence of this, is that everyone, me, you, everybody, we do not perceive the universe around us in the exact moment of time that we think we do. Everything that's around us, we are seeing a little bit older than it actually is. I'll explain that a little bit more. Again, from a terrestrial standpoint, it really doesn't matter. From a terrestrial standpoint, things happen pretty much simultaneously. If I see a car wreck over here, then that car wreck is essentially happening right now in my existence. With astronomy, we deal with distances so large that actually no longer becomes the case. So I'm going to start off with this image, which is called Earthrise. It is a very famous image, is almost iconic at this point. It was taken by, I believe, again, I hope not to embarrass myself, Fred Berman during the Apollo 8 mission, which was a mission, which is the first manned mission to essentially circumnavigate the moon. And this actually almost didn't happen. this image or this picture, they were looking somewhere else, and then one of them actually kind of looked out the side port window and said, "Oh my God!" And they're like, "Get the camera! Get the camera!" And so this was an image taken from the moon, from above the moon's surface, the lunar surface, looking back at the Earth. The reason why, there are probably many different reasons for why this is the most one of the most famous photographs ever taken. But in the context of what we're talking about, this is the first time that a human being has taken a photograph of the Earth from away from the Earth's surface, essentially away from the Earth's surface, away from low Earth orbit. Actually, I would hesitate. I would go on a limb and say this is the first time a photograph has been taken by a human being, not a satellite, but by a human being, from beyond the Earth, and definitely the first time the photograph is taken from the moon, at the distance of the moon. And you can see, as I kind of sort of illustrated with the pale blue dot perspective, you can see that even from the moon's distance, which is, again, astronomically speaking, fairly small, fairly short, the Earth is rather small, and in my mind, rather precious. So let's start off by asking, what is our place in the universe? And really, we're going to be asking questions: how big and how old is the universe? So let's start off with, what is your mailing address? What would your cosmic mailing address be? So obviously, you've got your street, you got your city, you got your country, so forth, so on. But then you can say, I'm on Earth, which is the third major body, third planet orbiting around the sun. The sun is in the galaxy, the Milky Way. It's about 2/3 of the way out from the center of the Milky Way galaxy. So now you live on Earth in the solar system, in the Milky Way galaxy. The Milky Way galaxy is in itself in the local group. A local group is a small collection, well, again, astronomically speaking, a small collection of galaxies with three major galaxies: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy, and then about 24 smaller dwarf galaxies, if you pardon the term, satellite galaxies. These are small, and they're all orbiting around a local center of mass, or a local gravitational center. This local group is then a part of something known as the Virgo cluster, which is composed of hundreds of, possibly thousands, of galaxies in and upon itself. And then finally, that cluster is located in something known as the Lunica supercluster. The superclusters are then in themselves located into this filamentary structure throughout the universe. Again, that goes beyond the scope of this course. But what I will say is that the Lunica supercluster, which contains hundreds of thousands of galaxies, is in and itself one of the largest coherent structures in the universe, and there are billions of them. So, just to bring back the point of what is your address? Your address is your street, your city, your street, your state, maybe your city, state, country, then the Earth, then the Milky Way galaxy, then the local group, then the Virgo cluster, and then finally Lunica and the supercluster, and then finally the universe. When we talk about the distances of these things, the distances grow very, very rapidly and get beyond incomprehensible, in my opinion. So let's start off small. Actually, I'm going to take myself out of this picture for a second. Let's start off small. How big is the moon? Well, if you the radii of the moon, or if you looked at the diameter of the moon, that would equate to about the same distance as the continental United States. Not quite. Basically, the distance from New York to Ogden, Utah. So not quite to the western coast. So the moon is, relatively speaking, much smaller than the Earth. But then if you look at the distance between the Earth and the sun, or the Earth and the moon, you're looking at 384,400 kilometers. You could take Saturn and its rings and actually put it between the Earth and the moon, and it wouldn't hit or touch the other. Obviously, from a gravitational standpoint, things would get really catastrophic if Saturn suddenly did appear between us and the moon. But that gives me an idea of something of an idea of just how far away the moon is. And also I want you to think about the fact that the moon, again, its size, it's not even the size, or the diameter is not even the length or width of the continental United States. So it's a small world, and it's 384,000 kilometers away. Going back to my previous lecture, one of the things I said was it is impossible to show the solar system in relative scale, or in to scale, in both size of objects relative to each other and distance of objects away from the sun and each other. Hopefully you can kind of see why that is the case there. Let me bring me back. Yay! Actually, let me take me out again. So one of the popular things to do is to basically scale things down and try to make scale models of things, so we can potentially visualize this. So let's imagine the Earth is the size of a marble. So, because I'm a geek, I have another visual aid. That'll work. This is a D12. So, yes, I play D&D. This is a D12. So let's imagine the Earth is that size. What would the rest of the solar system look like? Actually, what does the rest of the universe look like? If the Earth were yay big, then the moon would be located roughly there, away from it. The sun would be 1.5 football fields away. Neptune about 3 miles. Alpha Centauri, or Proxima Centauri, if you really want to get technical about it, would be the length of the Earth's circumference away. The Milky Way galaxy would be out to Saturn's orbit. Andromeda galaxy would be 20 times the solar system size, and Lioakea would be the same as the distance to Proxima Centauri, which is 4 light years away, approximately. Again, I will try to explain what exactly. If you don't know what a light year is, hold on to your hats. I'll be explaining what that is in a moment. So, yep, there we go. So let's take a moment to talk about numbers, both big and small. So, as I was just illustrating, things get real big real fast, and as I said, the distance to the moon is 380 some odd thousand kilometers away. So you can imagine how many kilometers, say, the distance from Earth to Saturn is. We're talking trillions of kilometers. The distance from the Earth to the sun is 149 million kilometers. So these are big, clunky numbers. Lots of zeros to have to write out if you were to have to. Particularly if you're doing any kind of math with it. So what do we use? We use something known as the scientific notation. And what this does is it's something of a shorthand that allows us to notate distance or notate numbers that are many orders of magnitude more than we're normally deal with, and many orders of magnitude smaller than we again normally deal with. Dr. Nimrod, howdy to you. I am doing fairly well. Just talking about the scientific notation. So I'm going to get a little bit into math, but hopefully I can make this clearer than mud. So the general form that number in scientific notation takes is a times the number 10 raised to the b power. So a squared number would be 10 to the second. A cubed number would be 10 to the third. So b equals 2 in the first case, b equals 3 in the second case. A is a number between, and actually I need to change this slide. A is actually a number between 1 and 9, or basically up to 10. So 9.999, but not 10. Every time you increment, and B is, B, again, I'm going to have to change this slide. In the context of what I'm going to be talking about, B is an integer, but B really can be any real number. So you can raise things to, no, I'm wrong. I'm thinking of just exponents. So B is an integer in scientific notation. So it could be 1, 2, 3, 4, 50, whichever. A positive exponent means essentially multiplying that a number, a value, by that order, that number of orders of magnitude. So if your b is 1, then you're multiplying that number by 10. If your b is 10, then you're multiplying that number by 10 to the 10th. So 10 orders of magnitude higher. If you have a negative exponent, then you're dividing by 10. Basically, what that means is that the number is getting smaller. So, for example, 10 to the minus 1 is 0.1. When you see a negative exponent, that does not mean the number is negative. So, for example, the vacuum of space is about 10 to the negative 17 torr. So not quite perfect, but pretty close. That does not mean the pressure is negative there. It just means that it's really, 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 really small. 10 to the negative 17. So how can we better, actually, yeah. Actually, I need to add something to this. I think I've forgotten a slide. So let me just try to talk you through it. So let's take let's take 1. All right, you have 1 decimal point. That would be A. A would be 1. B in this case would actually be 0. 10 to the 0 is 1. 1 times 1, 1. 10, an order of magnitude larger, or a factor of 10 larger, would be 1 times 10 to the 1. So what you've done is you've taken 1 decimal point. You've now moved the decimal point over to, I guess, to the right. Here it's my right. And now you have 1, 0 decimal point. 1 times 10 to the third, you have now moved the decimal point over. Or, I'm sorry, 1 times 10 to the second, you've now moved the decimal point over twice. So you have 1, 0, 0, period, or decimal point, or 100. 3 times 10 to the third, another decimal point. So you have 1,000, and so forth and so on. For a negative exponent, if you want to represent small numbers, then again we have 1 decimal point. If you have 1 times 10 to the negative 1, that means you move the decimal point over to the left. Your left, my left. So it's decimal point 1. If you have 10 to the negative 2, that's moving it to the left twice. 0.01. 10 to the 3, 0.001, or 1 in 1,000. So that's essentially how you work with scientific notation. So let's take a more practical example. As I said, the distance to the sun is 149 million kilometers. So what we would do is let's take 149. I know I said the A coefficient should be between 1 and 9, but for this, so just bear with me. You take 149, and then you have a million. Million indicates, or mega, indicates 10 to the sixth. So if you take 1 million, you're going to move that, in order to get it right next to the 1, you're going to have to move that decimal point over 6 times. So 1,000,000, 1,000,000,000 is actually 1 times 10 to the 6th. So if you have 149 million, 149 times 10 to the 6th, that's not the most appropriate way to represent things in scientific notation. You actually want to shift that decimal place over 2 more times. So it's 1.49 times 10 to the 6th plus 2, or 10 to the 8th. So what astronomers will say is that instead of saying that the sun and the earth are 149 million kilometers away, it's 1.49 times 10 to the 8th kilometers away. A little easier to say, much more easy to write, and much more easy to deal with. So I will come back. I know I'm flipping back and forth, but so let's say you had two numbers that are both in scientific notation, such as 6 times 10 to the 3rd and 2 times 10 to the 2nd. Or in everyday speech, that is 3,000 times 200. In scientific notation, what you do is you take the 6 and the 2 and you multiply them together to get 12. And then you take the 2 10 to raise to the powers, so 10 to the 3rd and 10 to the 2nd, and you add those exponents. So you now have 12 times 10 to the 5th. And again, as I was talking about before, you want to keep that A component, that first number, you want it less than 9. Or really, you want it less than 10, sorry. So again, you move that decimal place over. So instead of 12 times 10 to the 5th, you now have 1.2 times 10 to the 6th, or 1.2 million. If you were wanting to divide these numbers, 6,000 by 200, what you have is, you take the 6, you divide it by 2, you get 3. And then instead of adding the exponents, you subtract them. So now you have 3 times 10 to the 1, or 30. Hopefully that makes sense. Hopefully you can divide 600 by 200 and you get 30. Adding and subtraction, subtraction with scientific notation is a bit easier, in the sense that you really only want to subtract scientific notation that is in the same exponent. So when I talk about adding and subtracting, really all I'm going to be doing is, if I have 6 times 10 to the 3rd minus 2 times 10 to the 3rd, and then the answer to that is 4 times 10 to the 3rd. So let's go back to this. The International System of Units. What I like to tell my students, particularly when I'm teaching lab, is that units are absolutely important. Perhaps one of the most important things that you can possibly deal with when it comes to dealing with any kind of number. If you don't have a unit behind that number is meaningless and potentially dangerous, or shall we say catastrophic. For example, there was a satellite or probe going to Mars, the Beagle, I believe it was called, sent out by the UK, and it crashed into the surface of Mars because of a unit error. Instead of something being in centimeters, it was in inches. So units are vital, and you need to be consistent with your units. And the SI units, or something known as the MKS units, that is defined by looking at the 3 units of the basic quantities of length, mass, and time. M stands for meters, K stands for kilograms, and then S stands for seconds. So every basic unit, when we deal with astronomy or deal with physics, the lengths are always given in meters, the masses are always given in kilograms, and the time is always given in seconds. Because saying 10 to the negative or 10 to the 6th or 10 to the 15th is a little bit cumbersome, we do have prefixes that allow us to simplify things. From giga, which means a billion. So a gigameter is a billion meters. Kilo is 1,000, so kilometers means 1,000 meters. I skipped over mega. And then all the way down to micro. One of the things that I'm going to be talking about later, I'm going to be throwing around the word micrometer or micron quite a bit. And that is 1/1,000,000th of a meter, or 1 times 10 to the negative 6 meters. Because most of the wavelengths that we look at, visible light, radio light, or visible light, infrared light, things of that nature, the size of those waves, the size of that light is on the order of 1 to 10 to the negative 6, or a micron. So, last thing I'll talk about, say with this, is orders of magnitude. I've already been bandying around that number, or that term. And really what an order of magnitude is just a factor of 10. So if something is 100 times larger than something else, then I will say that that thing is 2 orders of magnitude larger than the something else. If it's 1,000 times larger, 3 orders of magnitude. So when I talk about orders of magnitude, really what I'm talking about is a power of 10. Now, astronomers, physicists, we kind of like to do what was known as a back of the envelope calculation. Basically, we just estimate. And sometimes we'll just kind of wash our hands and say, it's good within an order of magnitude, or meaning that it's good within a factor of 10. So, good enough for government work. My brother's a nanophysicist PhD in engineering or something. Very nice. Very nice. Yeah, I'm sure he is very aware of scientific notation and the nanometer, or 10 to the negative 9. Whoops. All right. There we go. Now let's talk about distance and time. Let's take this scientific notation and talk about how do we really apply that to distance and time. Well, first, let's talk about unit conversion. And the reason why we use unit conversion is that depending on the scale of things, astronomers will use different units. I mean, I said that the basic unit for length was a meter. That is true. But even if you're using meters, and even if you're using scientific notation, then that scientific notation can get really ungodly, really cumbersome to use. As I said, the astronomical, or the distance between the Earth and the Sun is what we call an astronomical unit. It is 149 million kilometers. I'm sorry, I've been saying million kilometers. It's 149 million meters, or 1.5 times 10 to the. No, it is kilometers. I need to fix that. But even still, the astronomical unit is good within the solar system. So instead of saying, 10 to the 12th or what have you, the distance to Pluto is 40 AU, roughly speaking, or 40 times the size of the distance between the Sun and the Earth. So it's a much easier number to work with. 40 is much easier than, say, 10 to the 11th, 10 to the 12th, something like that nature. But if we were to talk about the distance to Proxima Centauri, the AU then gets cumbersome again. It becomes, again, you will be having to use times 10 to some high factor. So now we go to that concept of the fact that light does not travel instantaneously. Light travels at 3 times 10 to the 8th meters per second, or 300,000, 10 to the 8th, I'm messing, 300 million, yeah, 300 million meters per second. Why does that sound weird to me? I think I'm embarrassing myself. It's 3 times 10 to the 8th meters per second. I know it is. Anyway, so 3 times 10 to the 8th meters per second. So what that means is that it takes, over the span of a second, a light particle, a photon, a bit of light, will travel 3 times 10 to the 8th meters, which is a really far distance. But, and we can extrapolate that to, say, a light year. So that would be a light second. Then a light day would be from how long it takes for that photon to go from one place to another in the length of a day. And then a light year is the distance it takes for that light particle to go from one point to the next in the course of a year, which is 6 trillion miles, or 1.5 quadrillion meters, or 9.5 times 10 to the 15th meters. So you can see that Alpha Centauri is roughly 4 light years away. So using 4 times, basically using, what would that be? 40, or 4 times 10 to the 16th meters, just to talk about the distance to Proxima, let alone something else that's hundreds of, or thousands, or millions of light years away. We simply use light years. Then we also use, if you really want to get into the nitty-gritty, astronomers actually prefer what's known as a parsec, which is a more, it actually derives from a particular form of measurement, which I will get into it later. Han Solo, don't know what he was thinking. A parsec isn't a unit of time. It's a unit of distance. And in this case, a parsec is 3.62 light years. Again, I will later be talking about what a parsec is, why it's 3.26 light years. But for now, just know that that a parsec is the preferred sort of long distance unit that we use. Yes, Dr. Nimrod. Distances are astronomically large. I see what you I see what you did there. So getting these distances, finding these distances, hasn't been really a trivial matter. In fact, it wasn't until the mid 1800s that we knew fairly accurately what the distance between the Earth and the Sun was, and we found that out through a nifty bit of geometry when the Venus transited across transited across the surface of the Sun. So we saw this black dot move across the surface of the Sun, or the apparent disk of the Sun, excuse me. And by figuring out how long it took to get there, to go across, we can then use geometry to figure out just how far away Venus is, and also the Sun, and then conversely, the Sun. I will be doing, I don't know when, but I will be doing a video, a separate video that actually talks about that process, because it's not a overly trivial, and it's a really clever bit of engineering or math to figure that out. So it's actually kind of cool. So I've been emphasizing how large things are, but also we have to emphasize how small things are, because in astronomy we deal with things that are astronomically large, but we also deal with things that are very, very, very tiny. We deal with the very fundamental building blocks of the universe: electrons, quarks, leptons, baryons, small atomic particles. So, for example, if you look at a proton, or you look at a hydrogen atom, for example, which is just simply a proton and electron going around it. The proton has a size of 10 to the negative 15 meters. So, as big as As big as a light year is in terms of a meter, a proton is as small in regards to that meter. So tiny. The orbit between the orbital size of the electron going around is 5 orders of magnitude larger. It's only 10 to the negative 10 meters, which actually, as a side note, is really fun to think about, because the size, if you were to compare the distance between the electron and the proton in a hydrogen atom, with regards to the sizes of the two bodies that are involved, the space between them is immense. If you were to say, take the ratio of the relative size, relative distance, that number would be tiny, much tinier than, say, if you were to take two local galaxies or two nearby galaxies and do the same thing. What that means is that our reality that we move around in is mostly, and I do really mean mostly, empty space. It's only because of the quirks of electrostatics and the fact that our eyes are small and cannot resolve things down to any sort of small distance scale that we perceive things to be solid. It's the electrostatic force that keeps my hand from pushing into this table. It's the fact that my eyes only have a size, or an aperture size, of around 8 millimeters. So I can't perceive that small distance. So, peak alert. Hi, Tina. I can't perceive the small distance between protons and electrons, and so it blurs out, and I perceive things as solid. But in actual fact, they're not. Actual fact, the universe around us is very, very spacious. So again, thoughts that you can have on the front porch of a friend's house while smoking. So if we go from orders of magnitude, there's actually a great, back from I think it's the 70s. You probably can find it on YouTube somewhere. It's called Powers of 10. If I think about it, I'll put it in the description, the link to it in the description. And it focuses on a couple laying down in a field, in a park in Chicago. And basically they say that the man is about 2 meters tall. So you start off with 1 meter, and then it increases every second an order of magnitude. And so it zooms out from the man to Chicago to the earth, so forth and so on. And you get to really sort of envision just how big an order of magnitude is. So if we look at it, we have that the Earth, or the human being, is roughly around 1 to 2 meters tall on average. Planets are about 10 to the 8th, or 8 orders of magnitude around their bigger. Then if we look at the luminosities, we see that the sun has, if we take the sun, I'm sorry, that's not, I really need, what is wrong with these slides? L is luminosity, not size. When you can see from these slides, I do apologize. I'm it's very unprofessional not to know this, know my own slides very well. But anyway, the point I'm trying to make here is the distance between galaxies, for example, is 10 to the 21. Between galaxy clusters is about 2 orders of magnitude larger than that. So if you were to look at the size of a human being compared to Luna Kea, the supercluster, you're talking about 24 orders of magnitude. To me, that's incomprehensible. I can barely envision what 3 orders of magnitude looks like. The difference between, say, 1,000 me and 2 kilometers. I can barely kind of wrap my head around that. 24, no, it's out the window. So, what about time? And what about that thing I was talking about in the fact that we don't perceive the universe as it is happening right now. What I mean by that is that the speed of light is the ultimate speed limit. Nothing can travel faster than that. Nothing can be communicated faster than that. If you think about it, everything we, well, not everything, the things that we see visually around us are communicated to us by light. For example, if when I look outside, I see construction workers. The reason why my brain tells me that there are construction workers out there is because light is being reflected off of those gentlemen and being directed to my eye. Light is telling me that those folks are out there. If I were blind, or if I had if there was an opaque wall here, there's something blocking that light, I would not know from visual context that those folks were out there. So communication can only travel the speed of light. That also includes gravity. Gravity only can travel at the speed of light. So, if you were to think about the sun is 8 light minutes away. Hey, Clive. Howdy. The sun is 8 light minutes away. That means that it takes light 8 minutes to get to us. It also means that the effects of gravity that the sun has on the earth, it also takes 8 minutes to get to us. So when we look at the sun, we're like, oh, look, sunspots are there. That's true, but if you want to be really specific or potentially pedantic about it, what really is happening is that those sunspots were there 8 minutes ago. We don't know what's happening right now on the sun. We know what the sun looked like 8 minutes ago. If Thanos were to snap his fingers and make the sun go away, we wouldn't know for 8 minutes. Now, a student of mine pointed out that, that's all well and good, but from a practical standpoint, it really doesn't matter. I mean, yes, that's true, but it's something you have to keep in mind, particularly when you're an astronomer. Because let's look at some light travel times, and I'll get rid of me again. The one I want to focus in on is the one again. I keep using Proxima Centauri. Takes about 4 years, or 4.2 years, or basically the span of a U.S. president's term of election. Takes 4 years to get there. So imagine that we had the capability that aliens existed on, let's say an alien cat was on the surface of Proxima Centauri, doing cute cat things. When we look at it and assume that we can see it, we can watch that cat do cute cat things, but that cat is not doing them right now. That cat is doing that 4 years ago. If we look at, let's say Betelgeuse, which is 40 light years away, we're seeing Betelgeuse as it was 40 years ago. And in actuality, it's not out of the realm of conception that Betelgeuse isn't there anymore. Betelgeuse can supernova anytime within the next 100,000 years or so. We can't narrow it down. Science cannot currently narrow it down any further than that. But it could, unlikely, but it could that that Betelgeuse has supernova, and we don't know yet because the light from that supernova has yet to get to us. The gravity from that supernova has yet to get to us. And it gets worse from then on. The more you look, galaxies and so forth, stars and then galaxies, you're looking at hundreds of thousands, millions of light, or possibly billions of light years. So when we look at galaxies, when we actually do studies of galaxies, we very much have to take this into account. Because again, if we're looking at these galaxies and we want to know, all right, what is this galaxy composed of? in the context of, say, how does a galaxy evolve with time? And if we look at that galaxy, we have to keep in mind that what we're seeing is the galaxy as it was 4 million years ago or 4 billion years ago. So we have to keep in context of how old it is when we see it as compared to how old it was when it was formed. So again, we're not seeing those galaxies as it is right now. We're seeing those galaxies as they were hundreds of thousands of light years away. Oops, I can tag. So just running through the basic, like I said, if you take light, travel the diameter of the galaxy, that takes 100,000 years. Light from the largest galaxy, Andromeda, to us, essentially the first, the Homo erectus humans were just appearing. So if we were to look at a Earth twin in the Andromeda galaxy and we were able to see the life forms on it, then if they were exactly in comparison to us, then we wouldn't see advanced humans on there. We would see Homo erectus. Again, the consequence is, and as my student pointed out, from a practical standpoint, it really doesn't matter. Hey, Jonathan. But there could be intelligent species, advanced species in Andromeda right now, but we don't know because it takes so long for that light to get to us. And really, that's also going to play a factor when we start talking about space exploration, solar system exploration. And I'll hammer those points home more specifically or in more depth later on when we actually start talking about Mars, how far away Mars is, and potentialities of life and habitability and so forth and so on. The thing I want to end with is I've been talking a great deal about size, distance. What about time? The universe is vast, again, as Nimrod pointed out, it's astronomically large. But in another way, it's also astronomically old. The universe right now, the best we can figure, is around 13.8 billion years old, or 1.38 times 10 to the 10th years. You can convert that into seconds if you'd like. So really old. Again, almost incomprehensibly old. So I think this is a trick that Einstein did, and I think Einstein actually did it in terms of a calendar year rather than a day. But if we look at the events of the universe, or the events of the universe as if we scaled it down to 24 hours, things get put into a certain perspective. So let's say at midnight, or just shortly after midnight, the universe came into being as we know it. Basically, a energy field, an immense energy field, is very hot, very dense, came into being. 2 seconds later, the first hydrogen and helium atoms were created. So the first normal, or what we consider to be normal, mass was created. Then, if I'm reading this right, yes, 10 minutes later, we have stars coming into existence. So comparatively speaking, material, the building blocks of material, were relatively fast in formation. In this sense, 2 seconds. Stars, and then galaxies, again, fairly rapid, about 10 minutes. It then takes a roughly 14 hours later for the solar system to come into being. So the first stars, 10 minutes. The solar system, 14 hours. And then about 5 minutes later after that, so it's now 4 p.m. So at 4:05, a Mars-sized impactor smashes into the Earth at a very oblique angle and then forms the moon. And then the Earth hangs out for about an hour or hour and 15 minutes. Then the first single-celled organisms, I do love teaching some cosmology. Then around 5:20 p.m., the first molecule, or basically very primitive single cell organisms, come into being. And then it takes the universe 3 hours and 20 minutes for more complex single celled organisms to appear. 4 hours, 20 minutes. Again, it took 10 minutes for stars to form. It took 4 hours and 20 minutes for life to go from primitive single cell organisms to complex single celled organisms. Then it takes about an hour later for multicellular organisms to come into being. And then the Earth life takes its sweet time, and about 2 hours later, the first animals start crawling their way out of the primordial soup. 15 minutes later, I'm not putting up that. I'm not highlighting that, Clive, but maybe. The first, so at 11:20, the first animals come basically crawl themselves onto land. 15 minutes later, you got dinosaurs. They get to stick around for about 20 minutes before an asteroid smashes into the Earth and kills them all, and mammals basically start taking over. The first human ancestors, the first hominids, show up in this scale at 11:59:20. So 11 hours, 59 minutes, and 20 seconds. So the first humans, as it were, or human beings, as it were, as a species. I'm not a biologist, so I'm probably getting that wrong, but I hope you understand what I'm getting at, is that the most basic human being, or human being progenitor, in the span of 24 hours of the universe, has only been around for 40 seconds. Then it gets worse. The first Homo sapiens actually appeared 0.15 seconds before midnight. So Homo sapiens have only been in the universe for 1.5 seconds on the scale of 24 hours. And then when you talk about modern humans, it's 0.2 seconds. So it's looking at this is kind of like looking at that pale blue marble. When you look at that, or pale blue dot, you look at that and you say, wow, that is really, really tiny dot in a vastness of black, and basically an open void, as it were. This is another way of kind of looking at that, in that the human race and everything, the modern human race, everything that are trials, our tribulations, things that are successes, our failures, the atrocities, the unbelievable acts of altruism, all of that has happened in basically the blink of an eye in terms of the universe's existence. The universe has been here for a really long time. We are not even the newcomers on the block. I mean, that's not we're even shorter than that. Wish I had a better way of putting that. But again, it illustrates that human beings, in the concept of the universe at large, we are very tiny, size-wise, and we've only been here for the blink of an eye. Again, to me, that indicates that we are precious, that we are something special in the universe. Particularly if you look at the dinosaurs. I mean, they got 20 minutes of fame before they got wiped out. So we got if that's an example, or if that's a kind of something to go on, we got a bit of time before something really bad happens, assuming we get our hands on this, or handle on this whole climate change thing. But I will not digress from there. All right. So that's basically it for my lecture today. Hopefully hopefully you enjoyed it. I do apologize for stumbling over those values in the slides. I will I will double check those and put some corrections. If they are incorrect, I'll put corrections in the description. So, but again, I hope this lecture went well. I hope you enjoyed it, learned something. And so now I will. I have a few minutes. I have a few minutes before I have to go putsy around with the observatory. I have lots of things to do, improvements to make. But so I'll stick around for a few minutes to chat, answer any questions that you might have. Oh, thanks, Pam. I appreciate that. I appreciate that. I hope to make them entertaining. I think that facilitates learning, as it were. Okay, now the coffee really is gone. All right, so I'll have to switch over to water. I also have to say that while I am a George Mason patriot, I am also at heart a Florida Gator. So that's where I did my undergraduate and got my master's. So next thing I'm going to be talking about, here, let me bring that up. Kill that. Where is it? My next lecture, which will be on Monday, I will basically be giving a tour of the universe. I will be basically just talking about, in very broad strokes. I will be discussing what's in the universe, or at least what we can see and measure in the universe. Planets, galaxies, so forth and so on. And I will also talk about some atomic particles and things of that nature. So again, it's going to be dealing with things that are very, very big and things that are very, very small. So hopefully you'll enjoy that as well. Now, I thought I saw one of our Jonathan's in the house. I don't know if he's still here, but he is one of our tour guides, one of the undergraduates here at George Mason. Fantastic. He does great work here. So I give a shout out to Jonathan. If you were to become a patron of my channel, the money that I raise from that goes directly into the outreach, specifically the Friends of the Observatory or the Astronomy Club here at George Mason that Jonathan is a president of. So I don't usually like shilling my Patreon, but since he popped up, it occurred to me, and so I thought I would put that in there. Do I have my own observatory? Me personally, no, I do not. The reason for that is that I have been blessed with, since being an undergraduate, I have worked at an institution that has their own telescopes, and telescopes that are far more expensive than I could possibly afford. So I've had the luxury of being able to use the telescopes at my workplaces. Like, for instance, here at George Mason, we have a few different telescopes. Our largest of which is a 32-inch Cassegrain telescope. So far better, far more fun to play with than anything that I could potentially afford. We also have smaller scopes, from 4-inch refracting telescopes to 8 and 12-inch reflecting telescopes. Again, Cassegrain telescopes. So, and a myriad of different cameras that we use. Granted, most of those cameras are now dated. Well, most of the telescopes are actually a little bit dated. I am at the risk of babbling. One of the things that I hope to do is use university funds to actually buy a couple of more 8-inch Schmidt Cassegrains for lab purposes. I want to get 6 of them. I want to get 6 identical setups, so that and then design labs around them, so that we have nighttime labs where students can then learn about not only how to set up telescopes, how to use them from a hands-on perspective, but also how to take astronomical data, actual data of say, variable stars or asteroids or what have you, and analyze that data in some simple way. Obviously, these labs would be for introductory type, like 100, 200 level classes. So freshman, sophomore would be the sort of target audience. So it would be very, very introductory. But that's one of my goals of being here at George Mason, is building that and providing that resource for students who come to our university, is to have that kind of experience. So that was a very, very long-winded answer to your very, very simple question of, do I own an observatory? I would love, if when I retire, I would love to have what Bob the Science Guy has. If I have enough saved up for retirement, I'm probably going to do what he did. He is doing. You should subscribe. You all should subscribe to his channel, by the way. All right. Well, I think I'm going to wrap up here. Like I said, I have some improvements to do with our observatory, which I'm really excited about, because one of my favoriteest things to do is play with telescopes. So, as I've said before. So, all right. Thank you all for watching. Those of you who are here today, and any of you who are watching in the future, thank you for spending your hour with me. I hope you do well. Clear skies and peace out.